になりましたので、ただいまから第7回エネルギー情勢懇談会を開催いたします。本日は飯島委員と五ノ上委員がご欠席でございます。それでは冒頭、最初に世耕大臣から一言お願いいたします。
皆さん、こんにちは。本日はご多忙のところお集まりをいただきましてありがとうございました。いつも挨拶だけして終わりだったんですが、今日は国会が少しお休みになりましたので、まとまった時間お話を聞かせていただくことができるというふうに思っています。また、ジョン・ホプキンズ CEO のホセ・レイエス CTO、そしてアルン・マジュマダール教授におかれましては、米国から、そしてこの懇談会のためにお越しをいただきました。そしてファティ・ビロル事務局長におかれては、フランスからお越しをいただき、後半からご出席をいただきます。はるばる日本まで来ていただいたことを心から感謝申し上げたいと思います。世界の国々はですね、パリ協定を踏まえて2050年を視野に脱炭素化に向けて動き始めております。再エネへの投資が拡大するとともに EV をはじめとした運輸部門の電動化、そして水素などの技術開発も進んでおります。一方で脱炭素化に向けたシナリオはコストですとか技術の動向によってまだまだ不確実な状況であります。これまでこの懇談会では内外の第一線でご活躍をされている経営者、有識者の方々をお招きをして、長期の需給シナリオ、各国の温暖化対策、エネルギー企業の戦略、水素、蓄電池、モビリティ戦略などさまざまな分野について議論を深めてまいりました。その共通項であり、2050年を語る上で欠かせない要素はやはり技術とイノベーションだというふうに思います。今日はですね、将来の原子力の可能性に着目をした技術の状況、AI、IoT などデジタル技術が電力システムや分散型エネルギー社会に与える影響、そして2050年へ向けた世界のエネルギー情勢について多くのご示唆をいただきたいというふうに思います。本日の議論を十分に参考にさせていただきながら、中長期の戦略と施策につなげてまいりたいというふうに思います。今日はどうぞよろしくお願いいたします。
ありがとうございました。それでは今回も前回と同様前半後半に分けて議論を進めたいと思います。まず前半は前回から引き続きましてエネルギー分野の次世代技術イノベーションの動向について2つのプレゼンテーションをお聞きいたします。大臣からもございましたが、米国のニュースケール社から来ていただきましたレイエス CTO、それからジョン・ホプキンス CEO から小型原子炉の技術の動向、それからスタンフォード大学からお越しいただきましたアルン・マジュマダール教授からエネルギーシステムに関する技術革新、この2つにつきまして、まずお話をいただきます。後半は IEA のファティ・ビロル事務局長から中長期的な世界のエネルギー動向につきまして、お話を伺って、取りまとめに向けた議論の参考にさせていただきたいというように思います。まず前半は2つのプレゼンテーションをお聞きしますが、資料3にございますように、事前にですね、2つのニュースケール社とマジマダール教授には質問事項を事前に投げてございます。脱炭素がカーボンフリーに向かえた技術の動向、見通し、あるいはその国に求める役割、それからそれぞれの分野における戦略、さらにその技術の動向等々について、どのようにお考えかということを質問として、事前に投げかけてございます。資料4は、事務局でまとめました次世代技術イノベーションの動向について整理したものです。これは前回もお配りした内容でございますので、説明は割愛させていただきます。それではまず、ニュースケール社のレイエス CTO、ホプキンス CEO からプレゼンテーションをお願いいたします。20分程度でできればお願いをいたします。
Distinguished members of the committee, ladies and gentlemen, thank you so much. It's an honor to be here to share with you this information on our innovation of our design. So I am Jose Reyes, the Chief Technology Officer and co-founder of NuScale Power. And with me today is John Hopkins, our Chief Executive Officer of NuScale. I will focus on the technology, and John will focus on the economics. So we hope to have a good discussion with you today. Thank you again for inviting us. It is truly a great honor. There are many slides in this deck, about 40. I'll only be covering about 10 slides, okay? So there's a lot of information which is available for reference that you're welcome to look at, but I'll just cover a few select slides. It's been said that the best way to predict the future is to invent it. So NuScale is an innovation company, and what we do is we have a focus on people, planet, and prosperity. Our mission is to provide a scalable, advanced nuclear technology for the production of electricity, water, and heat to improve the quality of life for people around the world. So that's our mission statement. On slide 3, it describes our company just a little bit, but basically the development of our design started in the year 2000. I was a professor at Oregon State University, and this is what was part of our research program there. And it really started from a clean sheet of paper. So I was able to adopt all the lessons learned. I had worked for the NRC for 10 years. I'd been at the university for 30 years. And to come up with what we believed was the safest nuclear energy system design that was possible in the world. I co-founded NuScale Power in 2007. And I started with 3 basic fundamental patents. And because of all the innovation that's happening, we have many young engineers working with us in our company. We now have over 400 patents, either pending or granted in 20 countries. So lots of innovation, very exciting time. About 800 engineers working with us on this project from the beginning. We're the first small modular reactor to have submitted a design application certification, design certification application to the U.S. Nuclear Regulatory Commission. And currently, we're the only SMR under consideration in this review process. To date, we've invested, or have invested, $700 million. So this technology and the design has advanced significantly. We've had funding both from private investors, primarily Fluor Corporation, and from the U.S. Department of Energy. Our current plan with our first customer, which is the Utah Associated Municipal Power Systems, UAMPS, we're on target right now for the first commercial operation in the year 2026. So it's not too far from now, but it's been a long road up to this point. So I'm going to jump and describe the technology a little bit. And so the easiest thing to do is to show a video. So I'll ask for that video, and I can describe that process. So this describes, just at a very high level, this is our reactor module, which has the reactor vessel inside of a containment vessel. And this has sound, I guess. It's a light water reactor, pressurized, that operates under natural circulation. So the control rods withdraw. We generate heat in the core. It heats up the water. That water rises because it's less dense than the cooler water. So you have a density difference, elevation difference, which drives the flow. This design does not have reactor coolant pumps. It is driven solely by natural circulation. As the water turns the corner at the top, we have 2 helical coil steam generators, which removes the heat. And so the cooler water comes down, and the hot water comes up, and so you establish a natural circulation. Now, I've built this at 1/3 scale, and we've performed significant testing to demonstrate that this works quite well. On the secondary side, we do have pumps. We have a feed water system, which provides water into the inside of the helical coil tubes. That water is boiled to steam. Superheated steam leaves the reactor, goes to the turbine generator set. So here's the turbine generator. This is skid mounted. So it's available in the fossil fuel industry. Each of these skid-mounted turbine generator sets is 50 megawatts electric. So it's carbon-free, 50 megawatts electric. It's a standard ranking cycle, so it should be very familiar to most everyone. This is our condenser box. That condenser, because it's small, it could be either water-cooled or air-cooled. In many regions of the country where we're having discussions, they don't have sufficient water, and so they need an air-cooled system. And so this would allow us to site these plants away from sources of water. Feed water pumps take the water back from the condenser into the lower channel head of the helical coil steam generator. And that water boils inside the tubes, and that cycle just repeats itself. Okay. Thank you. So we're going to jump to slide number 13. And I'll describe the layout of the building. This is the current design that we're licensing with the Nuclear Regulatory Commission. It is a 12-module plant. So each module produces 50 megawatts electric, 12 modules for a total of 600 megawatts electric in the plant. So even though the modules are small, you can add modules to increase your power as power is needed. At this point, the modules have been manufactured in a factory. They're shipped in 3 to 5 pieces to the site, either by truck, rail, or barge. The fuel is shipped separately. And what we have is a module installation. So the construction is complete, and now we're just installing modules. So this shows one module being delivered, 5 modules in their individual bays. And this is a cross-section, so there's another 6 modules on the other side. During normal operation, the reactor and the containment vessel sit underwater in this pool, a shared pool, and it sits below ground. So that's significant. So the below ground underwater design gives us a significant seismic capability. So this building is a seismic Category 1 building. This pool serves as our ultimate heat sink for safety. Everything that you need for safety is inside this building. And I'll describe a little bit more about that, but we don't rely on any external power or external water to provide an unlimited coping period for this design. So it's very different. We worked with 29 utilities currently in our NuScale Advisory Board. They've given us a lot of input into the design. They like the idea that each module has its own dedicated turbine generator set. So what that means is you can add modules as modules are needed. It also means that when we refuel, we can refuel in a staggered manner. So we can take one module, put it into the refueling pool, perform the refueling operation, while the other 11 modules continue to produce power. So this plant will produce power 24 hours a day, 7 days a week, and you only lose 50 megawatts for 10 days for the refueling and maintenance. The other ability with this is that because it's a staggered refueling, you can have a very small in-house crew perform the refueling outages, which means instead of bringing in, as is done typically in the U.S., 800 to 1,200 contractors, putting them through security clearance, giving them health physics training, what we do here is we have a permanent dedicated crew. There's only 37 fuel assemblies per module. So the refueling process is very quick, and the maintenance can be done at this location where we have the refueling area. It eliminates the single shaft risk. Today, with large nuclear power plants, one of the challenges, you have a small part on a turbine. That part breaks, and you lose 1,000 megawatts off the grid. Here you have multiple turbines, so you only lose one module, and you continue producing 550 megawatts instead of the 600. In terms of the seismic capability, I will mention that this, because it's below ground, our analysis indicate that the peak ground acceleration for the frequencies of interest to this building is in excess of 1.1, almost 1.2 G. So it's a very, very robust system. That's between the 3 and 12 hertz range. The zero period acceleration is about 0.5 G. So depending on how you do your comparisons, that's a significant improvement in seismic capability. This is just showing the layout of a 12-module plant. We are also investigating two modules and 4-module type plants. But the total acreage is basically 0.14 square kilometers. So let me talk now about safety. A couple of important features. First, because you have a cylinder, if you take a cylinder and you reduce the diameter of that cylinder, for the same wall thickness, you can significantly increase the pressure. So what this means is for our design, we have a design rating of close to 7 megapascals for our containment. So this is about 10 to 15 times the pressure rating for a conventional containment. We also have a vacuum inside containment, which allows us to eliminate the need for insulation on the reactor vessel. Also, because there's very little oxygen inside the containment during operation, if there is a release of hydrogen, you can't get a combustible mixture of hydrogen and oxygen inside containment. So this is a very important feature of the design. This is our key. We speak about passive safety. This is what I would call passive safety in the extreme. What we've done is eliminated the need not only for AC and DC power, but as I described, it is a totally passive system. So as I mentioned, each module, all 12 modules reside in the pool, which is the ultimate heat sink. Because the core is small, 160 megawatts thermal, when the reactor shuts down, the control rods come in by gravity. You immediately drop to about 10 to 11 megawatts within about a second or so. In a day, that decay heat has gone down to about 1 megawatt. So similar to one of the training reactors at a university. If we did nothing, if you didn't add water to the pool or cool the pool, and you just stepped back, from a period of 3 days to 30 days, very conservative, you'd see some boiling in the pool, but you would continue to remove the decay heat. After 30 days, you're down to 400 kilowatts or so of decay heat being produced. Air cooling by itself is sufficient to remove all of the decay heat. So we've gone from a water-cooled system to a two-phase boiling system to an air-cooled system. And what's very nice about this is that the nuclear fuel remains cooled for an indefinite period of time, unlimited period of time, without any computer action, without any operator action, without any AC or DC power, and without the need to add water in the future. So this is a very robust design in terms of safety. And I think it's, at least in the commercial nuclear power, there's nothing like it at this time. We talk about reducing plant risk. So in terms of safety, there's two aspects. The risk, which is made of two parts. The likelihood of an event, which is measured in terms of the core damage frequency, and the consequence of an event. So the first thing we did was we greatly reduced the likelihood of an event. So what this chart shows is the current fleet of nuclear power plants. This is in the U.S., this is the NRC goal, that you should not have a core damage event more frequent than once every 1,000 years. Excuse me, 10,000 years. What we have here shows that the existing PWRs, boiling water reactors, the new active light water reactors, the new advanced passive system plants, they all meet the goals with a significant margin. And because our design is so simple, we have very few valves, and we have significant redundancy in our systems. We typically fall within the range of 3 times 10 to the minus 10th and up to 3 times 10 to the minus 9th. We redo this analysis every quarter as we advance the design with actual information for our components. Now, we can say, well, once every billion years you'd expect to see an event that causes core damage. The next question was, well, what happens if you have the worst case conditions at this plant? And what we found was because we have additional barriers to fission product release, we have the reactor vessel inside the containment, and normally the containment sits in the atmosphere, exposed to the elements. But our containment sits underwater in a stainless steel lined concrete pool with a biological shield, and on top of that, it resides inside of a seismic category 1 building. What this means is in our analysis of emergency planning zone, we are able to demonstrate that at the site boundary, for the worst case accident conditions, we do not exceed the regulatory limits. So this is a huge milestone for us. Instead of the 16-kilometer radius emergency planning zone, we're saying we don't need an emergency planning zone. We can work within the commercial guidelines, and everything that is needed for safety is within the fence of the plant. So this is a significant step forward. Now, we've submitted this information to the regulator as part of the Tennessee Valley Authority submittal for their early site permit. They're looking at building a plant at the Clinch River site. And so as part of that, they were looking at emergency planning, and they included our analysis and calculations, and that's been submitted as part of that applications. Thank you. So this is a press release that they issued indicating that major event. We've completed about $70 million of testing with lots of international collaboration with Italy, Canada, France, Germany, and we're always open to collaboration. And as I'll mention later, Japan has tremendous capabilities at its universities, its national laboratories. I did work at one time with back then it was JERI, but now it's, I guess, the Japan Atomic Energy Agency. Tremendous facilities, world-class facilities. I worked with them on the AP600 many years ago. We've got a new level of plant resiliency, so I'll let you look at those slides, but the fact is, if you lose the grid, any one module can pick up the entire load for the rest of the plant. So your plant can be at hot standby conditions. As soon as the grid is available, then it is ready to provide power to that grid. So John is going to talk about the economics during our question and answer session, if you have any questions. I did want to go to this slide here. One of the things that we've also looked at is multiple applications for nuclear. I think one way to accelerate the decarbonization process is to not only use nuclear for electricity production, but also for other applications. So we did a joint study with the Idaho National Lab looking at desalination, at hydrogen production. And what we found was that a 6-module plant coupled to their high-temperature steam electrolysis would produce roughly 200 metric tons of pure hydrogen per day. We've also done a load-following study with our first customer. Many of the utilities have wind farms. They also have solar farms. And one of the challenges that these utilities have is grid stability. So our design, we've come up with 3 different ways to perform load following. So with our plants, again, because it's small and modular, we can actually follow the load to balance the grid. So this works very nice in integrating renewables with nuclear. And we can do this because, again, this is relatively small modules, and you have different ways of doing that. And I can talk more about that if you'd like. And with regard to the regulator, communication. That is essential. We actually opened an office directly across the street from the Nuclear Regulatory Commission in Washington, D.C. We submitted a 12,000-page design certification application, which describes our design. And that application is available. That application is available online. So if you have something to do this evening and you want to read through 12,000 pages of design information, you're welcome to do that. That is available on the NRC website. And so I'll close with this slide here. When I saw the questions regarding Japan's plans for decarbonization, I recognize that Japan is an ideal fit, at least for our technology, in support of decarbonization. What I find is that you have a very strong existing infrastructure for nuclear plant licensing and regulation. There will be a need, you would need to have some new regulations for specific for SMRs, but certainly our regulator has been very open in sharing that information. I think there's also, you also have very strong manufacturing capabilities. So these are relatively small forgings, easily within the capabilities of your manufacturers here. And so this represents potentially a new SMR industry for Japan and the Asia market. You have significant expertise in commercial nuclear power construction and operation. Again, that's a very strong feature. You have world-class, and I mean world-class, nuclear power testing and research capability at the Japanese national laboratories and universities. And we would be most pleased to collaborate with you in the different research areas, as we've done with Italy and Canada and other organizations. I believe there's an opportunity there. There will be a need to get this socially accepted within Japan. I think the national government will need to be committed to nuclear energy and to education of the public. So with that, I'll conclude, and looking forward to hearing your questions. Thank you.
レイテス CTO ありがとうございました。引き続いて真島ダール教授からプレゼンテーションをお願いして、その後にまとめてご質問させていただきたいと思います。それでは真島ダール教授お願いします。
Well, first of all, Mr. Honorable Minister, Mr. Commissioner, Mr. Ozawa, first I'd like to thank you for inviting me. I'll go out there. Okay. So thank you very much for inviting me. I also like to take this occasion to thank Mr. Tamoki Nakanishi and his team, Ueda and Tomozawa-san, who have helped very much in this trip, and also Mr. Furukawa of NEDO and his team of Dr. Yabe and Kameyama. When we talk about energy, and I'll speak from my experience, both in academic research as well as in the government. I used to be in the Obama administration in the Department of Energy, and also in the corporate world at Google. And the way I look at it, when we talk about energy transformation, which is, I think, what we are going through, it is very important to have the balance between security, affordability, and the environment. If you lose one, it's just not sustainable in the long term. So with that in mind, I think it's important to look at this transformation, and I'll talk about innovation. There's a lot of discussion in innovation. I want to focus on what kind of innovation. So I want to take you back a little bit in history and what was life like 200 years ago. We used to go in horse carriages and use oil for lighting. And 250 years, which is in the history of humankind, is a very short time, but it's completely transformed. We use 300 or 200 horsepower in our cars, in a Shinkansen about 10,000 horsepower, in our planes about 100,000 horsepower. And for lighting, we use electricity. This could not have been imagined 200 years ago. In a paper that Stephen Chu and I wrote, we called this industrial revolution from horsepower to horsepower. And I think a lot of people are now trying to understand which innovations will shape the next 50 years or next 100 years. And I think it's important to go back and see, how did we go from horse carriages to cars? And in any innovation, in any existing technology, the more we do, the cheaper it gets and better the performance. If you take horse carriages, people made lighter horse carriages, people made better wheels, better bearings, stronger horses. And we can go down that path. It's very important innovation. But at that time, there were some transformational ideas of changing mobility by cars. And initially, those technologies may be transformational, but they're expensive. And many of them fail. But failure is part of innovation. But those transformational ideas, some of them, not all, but some of them have the potential to become cheaper, better, faster. And that is the innovation that is both transformational and disruptive. And I believe at this point in time, for the last 100 years, the energy industry has been quite stable. We are now in the position to ask the question, moving forward, what are those transformational and disruptive innovations that we should be looking at? And what are we in the process today? I think we all agree that one of the major transformations that has happened, and this has happened in North America, in the United States, Canada, and Mexico, is that of unconventional. That has changed the ballgame. OPEC does not control the price of oil alone. We have a knob as well. And this has led to a tremendous amount of LNG trading, access to natural gas. And the question we can ask is, how much more can happen? How cheap can it really get? Today, we extract about 15 to 20% of the hydrocarbons, leaving about 75 to 80% down below. If we increase the effectiveness of hydrocarbon recovery, the cost will come down even more. And that is where we are in that process of disruption going on as we speak. At Stanford, we have a natural gas initiative to look at upstream, midstream, downstream, as well as LNG trading, economics, and geopolitics of natural gas. The next big revolution that we are in the middle of is that of renewables. And in renewables, 10 years ago, when I was in the Department of Energy, we never expected it to get this cheap. And this is happening in 1 decade. And the question is, how much more room is there? If you look at the performance of wind and solar, there's tremendous opportunity to go down even more. It will become one of the cheapest ways to produce electricity. And you're seeing globally this adoption of solar and wind. The challenge is not so much the cost of electricity generation, but its integration on the system. Because the grid, electricity grid, was never designed. I call the electricity grid of today the Tesla-Edison architecture, that were never designed for fluctuating solar and wind. It was designed for thermal power plants, as we just heard. So how do you adapt the grid? And it's not just the cost of generation, but the cost of integration that is important. I'll come back to that later on. At Stanford, we think this is a very important topic. And we also think that in addition to the renewable revolution, this other revolution of digital, which in Silicon Valley we are surrounded by this, will have major impact on the energy automation. Because in addition to the fluctuating generation, we're also getting a lot of distributed energy generation, whether storage, whether loads, which are all networked. And so the volatility at both ends of the grid. And we cannot manage this grid by phone calls anymore. We have to have automation. And the timing of the digital world is extremely important because now this is the time to put that all together. So at Stanford, we have started an initiative called Bits and Watts. Watts is about energy, bits is about data. And it is to manage this volatility and provide new kinds of services to the electricity transformation. This is not just a technical problem. This is a regulatory issue. It's a market issue. It is a business model issue as well. And we're trying to look at it as holistically as possible. The other revolution is that of storage. 10 years ago, the cost of lithium-ion batteries was about $1,000 a kilowatt hour. Today, that battery pack is $200, a factor of 5 in a matter of 10 years. How low can it go? There's tremendous room to go below, and I'll show you the data on that. So as far as transportation is concerned, we can see the roadmap to get to about $100 a kilowatt hour within the next 5 to 7 to 10 years. And at $100 a kilowatt hour, electrification of transportation, electrified transportation, is as cost-effective and range competitive as gasoline-based cars. and you give it another 20 years, we're going to see deep penetration of electrified transportation. How far can this go? How long can this happen? Today, the batteries are made of materials like graphite on the anode, as well as on the cathode is cobalt, nickel, and manganese. That's today's world. If you add a little bit of silicon to the anode, which is now happening, you tremendously increase the capacity. Silicon can hold 5 times more lithium than graphite. And that is happening right as we speak. If you change the cathode from the cobalt, nickel, and manganese to sulfur, you increase another. So we see tremendous change that is coming in the battery world beyond today's lithium-ion battery. Is that enough? I think for transportation, we can see it being cost competitive, but not for grid-scale storage. For grid-scale storage, you can use lithium-ion batteries for maybe at the most 4 hours. We have the technology, or it's in sight. If you want to go to 8 hours, it's not cost-effective because renewables may be cheap, but if you don't have the backup or don't have the ramping that nuclear can provide, it is very hard. And for multi-day, it cannot be lithium-ion. It has to be something cheaper like iron or sodium and sulfur. And that technology is still being developed to the point of cost and safety that we need. So this is a tremendous amount of R&D that has to go in to bring the cost down to make it safer. We don't talk enough about low carbon fuels and chemicals. One of the most important way to address the needs of the future when we are fluctuating energy is, can we turn renewable energy into hydrogen? Hydrogen, extremely important, and the source of hydrogen is water. Today, it is at about $5 a kilogram of hydrogen. It needs to be at $2 to be cost competitive. For that to happen, renewable energy has to be cheap, less than $30 a megawatt hour. And this is the first time in history now, and in the next 5-10 years, that carbon-free energy is that cheap. Never happened before. So the timing is tremendous. The challenge is the pathway, the electrochemical pathway, the thermochemical pathway. Can we figure out processes that can produce hydrogen from water with that cheap? We don't know how to do that at that cost level. The other one is that of converting methane, which is low carbon, to methanol directly. We don't know how to do that. That requires R&D. Because once you get to hydrogen and convert CO2 to some fuel, or you get to methanol that we don't have to refrigerate like LNG, the cost of transportation and the infrastructure for transportation of moving that fuel is already there. It's at 2 cents a gallon. So the key is to convert low carbon energy into liquid fuel, because that energy density is significantly higher than that of batteries. And we really have to focus on that if you're planning for the long term. So if you look at the options that we have of how to decarbonize cost effectively, there are a few options. One is to fuel switch from coal to natural gas, and with global access to cheap natural gas or low carbon fuel like methanol. The second is to decarbonize the grid by integrating renewables cost effectively, but also to reduce the cost of nuclear energy. And also, let's not forget carbon capture and utilization and sequestration. The third is to decarbonize transportation, certainly by electrification. But there's also a way to do that. It is very hard to electrify air transportation or long-haul trucking. We need liquid fuels, and that has to be low carbon, whether it's hydrogen or methanol or some zero net carbon fuels. We need R&D to get there. It is extremely important to find alternatives to industrial heat. Industrial heat is probably the most difficult thing to decarbonize. Whether steel manufacturing, concrete, or petrochemical, and then food wastage is the third largest source of carbon emissions. Third compared to China, United States carbon emissions, and then food. It's that big in terms of food wastage. Finally, energy efficiency and conservation. Just to one point out there, cooling technology is going to be extremely important in the future because most of the economic growth and population growth is happening in the tropical regions. And HCFCs, or the refrigerants of today, are going to be phased out. And we need alternative technologies for cooling. And we need innovation for that. And that's going to be disruptive as well. So if I look at the whole energy scenario, we are at a tipping point of a major transformation over a span of about 100 years. For 100 years, we have built our infrastructure on oil, gas, electricity, and our distribution system. And that is being questioned right now because of decarbonization, digital automation, as well as just diversification. And it's very important that we look at innovations, transformational, disruptive innovation, balanced with incremental innovation. Not just in technology, but in the other part, the policy part, is so important. To drive the technology, to adopt the technology is extremely, and they have to be coherent, because if they're fighting, you're dissipating energy. My friends in METI asked me to talk a little bit about an agency called ARPA-E, which is the DARPA-like agency within the Department of Energy. And I was honored in the Obama administration to be the founding director of this agency. And they asked me to talk about what is the mission, how was it successful, how did it do innovation. So I'd like to spend just a few minutes on this issue. This was created like DARPA. DARPA was created in 1958 in response to Sputnik, where US felt there was a threat in the Cold War. And out of the DARPA innovation came the internet, stealth technology, and many other defense and information technology. ARPA-E's goal is to do that for energy in the United States. The number one thing is very high clarity in mission. The mission is very simple. Reduce emission, reduce imports, increase efficiency of the economy. And to do that, to ensure US leads in the energy, advanced energy technology. It's the global competitiveness. That's part of the ARPA-E mission. And to look at the transformational and disruptive innovation. Because we had a lot of work going on in incremental innovation, we need the transformational disruptive as well. That was my job to set up this agency, which I did. This reported by law directly to the Secretary of Energy, with nothing in between. So I was reporting directly to Stephen Chu, and in addition to that, I was also, he asked me to become the acting Undersecretary of Energy. So I was reporting to, but it was an idea to bridge the gap within the Department of Energy between the disruptive innovation, transformational, and the incremental innovation. That was the idea. Just a few examples of what it did. If you recall, in 2010, 2011, there was a time where critical materials for rare earth magnets was becoming a geopolitical issue. We saw that in the United States, and we felt that this was a supply chain problem even for the United States. Because for magnets, the rare earth magnets, you need that for generators, motors, etc. So we looked at that and said that we need technology to be disruptive to rare earth magnets. And so we created a program called REACT, which is Rare Earth Alternatives to Critical Technology, where we said we will develop magnets which does not use any rare earths, and the performance and cost is better than today's rare earth magnets. If you do that, then you never need rare earths. And we put, it needed a program manager like, program director like Mark Johnson. We put about $25 million behind it, 14 projects, and out came new materials for magnets that completely changed the ballgame for these motors and generators. So this is the kind of disruption that we needed for our own energy security. Along with that, we put about $500 million, and there are about many, each program have 15 projects. I won't go into the detail in the interest of time, but these are various projects across the transportation and stationary power sector. But these are all those transformational ideas which have a potential to be disruptive in the future. Let me stop here. Thank you very much for your attention. Happy to answer questions later.
真島ダール教授、ありがとうございました。それでは、ここから、自由討議に入りたいと思います。ゲストスピーカーに対するご質問等、あるいはもちろんご意見でも構いません、いただければと思います。ネームプレートを立てていただければ指名をさせていただきます。それでは枝広委員お願いいたします。
ありがとうございました。それぞれにご質問させてください。まずニュースケールの原子力の新しい小型のものについてなんですが、これその地下に入れるので安全だという話でした。これが適している地盤とか、例えば日本は非常に地震が多い国なんですが、そういったことを考えたときにどういう適地を考えていらっしゃるのかというのが一つ。それから他の方からもご質問同じように出るかと思うんですが、この原子力発電所で発電するときの発電効率とかコストとか、もしくはこの方式でやった場合の核廃棄物、これについてはこれまでの従来型と何か差があるのか、強みがあるのか教えてください。それから真島ダールさんにも2つ教えていただきたいことがあります。一つグリッドが、過去のもので、変動に耐えうるものではないという話がありました。今日本では再生可能エネルギーを増やそうとして従来型のグリッドをなんとか太くしようと、今のネットワークを太くしようとするのと同時に新しいもっと分散型のネットワークも作らないといけないと、この両方進めないといけないという状況なんですが、何かそれのいい進め方のお手本のような事例があったら教えていただきたい。もう一つはですね、2050年のエネルギーの状況を考えている委員会ですので、この、ビッツ&ワッツのデジタル化によって、エネルギーをよりよくコントロールしていくという、これの技術もしくはいろいろな技術開発の中で2050年を睨んだときに私たちが何か参考にできるものがあれば教えてください。以上です。
それでは順に、レイテスさん、それから真島ダルさん。
Thank you so much for your questions. With regards to the seismic question, this is a below ground application. We had to do several things for this design, which required advanced analysis. So we developed some of our own analysis tools to look at soil structure interaction. And that's been a very good research process, and we've been able to benchmark that against existing codes. So that's a very if new designs are to go forward, they need to develop those tools. With regards to our particular design, we looked at hard rock designs as well as soft soils. So a whole range of different combinations. Each site will be a little bit different, and for our design. Site-specific seismic has to be done also. But we have done bounding analysis, and for us, for our building design, which is in terms of the seismic requirement, the peak ground acceleration we've designed for is almost 1.2 G. So in terms of seismic robustness, that's a significant improvement in seismic. For the higher frequencies, it's 0.5 G, which is comparable to what it's typically in the US we designed for 0.3 G at the zero period acceleration. We've designed for 0.5 G. So it does provide some advanced technology. The other thing that we had to develop in our tools was the effect of the water on the modules. And that was very interesting because that also served to dissipate energy. And we've seen some benefit from that. The second question was with regards to economics and efficiency. We're basically very similar in terms of thermal efficiency, somewhere in the 33% for this design. It's really very simple. We do produce superheated steam, so there's no separators or dryers on our secondary side. There's no moisture separator reheaters, so we've really reduced the cost by going with this very simple design, but the thermal efficiency is very similar. What's interesting is that we've done this without any requirements for pumped flow. So under natural circulation, you have lower flow rates, your heat transfer coefficients are lower, but because we went to helical coil, we have a large surface area per unit volume. So we're able to remove a significant amount of heat and keep thermal efficiency comparable with other designs. With regards to nuclear waste, we're using a standard 17 by 17 fuel assembly. Areva has manufactured that assembly. It's 2 meters in length. We didn't want to go to a different fuel type at this time because we want to keep it within the current regulations and within the current plans for waste disposal. In terms of the cost, you asked about the cost, and I'll turn that over to John.
Yeah, Jose mentioned this process started in the year 2000 with the Department of Energy under a program known as the Multiple Application of Small Light Water Reactors. The challenge for him at the time was better, faster, with extraordinary safety. It was not about commercial viability. I led the due diligence effort with Fluor Corporation in 2011. Our focus as a publicly traded company, could in fact these units be commercially viable? So we have targeted teams that do nothing but look at cost avoidance and how to get the design down without an impact on quality and that extraordinary safety. So the company I came from was an engineering construction company, no different hardly from JGC, Obayashi, or others that we has partnered with in many occasions. The first thing we did was a 15,000 line item bottoms up estimate to look at the overnight cost of this plant. In the United States, we have one competitor right now. It's, as the professor mentioned, it's natural gas. When you're at $2 or $3 per million BTU, our break even is normally between $4.80 to $5 per million BTU, which in the United States, what we have to do is figure out how to reduce that cost for our first customer, and it has to do with government intervention, production tax credits, loan guarantees, and as well as working with our existing supply chain to continue to push those costs down.
Professor Herrero, thank you very much for that question, because I think that's one of the most important questions today is about a grid infrastructure. As I said, the Tesla Edison architecture was never designed for this. So we are looking at not just the cost of energy, but the cost of synergy. That's the key in the future, because that we are getting into the world of ramping. Because the fluctuations, something else has to back up, and we need to account for that cost when we integrate renewables. So the cheapest way to do so is long-distance transmission from where the energy is being generated to where it is being used. In the United States, we are fortunate to have different time zones, and that helps, except that in the United States it's very difficult to build transmission lines. The second part is, what is the next cheapest? The next cheapest is pumped hydroelectric, which is on the order of $10 to $20 if it's retrofitting, $10 to $20 a kilowatt hour. If it's not retrofitted, it's about $100 a kilowatt hour, built from new. That's the other way to ramp up, but it has to have the capacity. And most of our hydro got built because of nuclear. And now we have to retrofit them. I believe maybe similar in Japan as well. The third one today is natural gas for ramping. And a lot of people say we can get to 100% renewable. That is true, but that's not cost effective today. So we need a transition plan. And natural gas can provide the transition, except that it has carbon emissions. So how do we get to a different kind of future? Either we produce carbon neutral methane or methanol, which I think is very important for a variety of reasons, not just for transportation, but for this, or we produce cheap batteries, or we have both. And I think planning for the future, it is very hard to predict exactly what's going to happen in the future. So what we really need to do is to look for options. Optionality is very, very important right now. And that will require not just the R&D part of it, but the policy angle as well, to try out experiments, because we are entering a world where there is no data from the past that we can use to learn for the future. This is new for all of us. In terms of the 2050 and bits and watts, we think that we are entering now a major revolution in automation. And that is enabled by distributed computing, networking, as well as algorithms which can learn, that we call machine learning, deep neural networks. There are lots of names for it, artificial intelligence. And these can learn better and faster than humans in terms of technical thing, not emotional, but technical. And I think this is, if we don't leverage this world of automation, we'll be left behind, because that can be utilized for a very positive thing, for managing this volatility of distributed network devices. When you have, distributed system that is generating, storing, and using energy in so many different places, it needs a level of automation that humans cannot do. And normally that has been done by using the data and directly doing control optimization. We have to look at, can we store the data? Can we learn from it? That's the world we're entering right now. And it is not a surprise that AlphaGo can beat the world champion of Go. And where the Go world champion has said, I never saw anything like this before. This is unique, this is new. And that will, I think, come into the, and the question then becomes, what is the regulatory framework? What is the business model to provide new services to the consumer? And I think we don't know that yet. This is the world we're entering right now.
ありがとうございます。それでは山崎にお願いします。
はい、どうもありがとうございます。それぞれにご質問させてください。で、まずニュースケールさんのレイエス CTO とホプキン CEO ですけれども、ユタ州が最初のカスタマーだということでお話をいただきました。スライドの中には、例えば風力との統合研究ですとか、あるいは多様なエネルギープラットフォームとしてのイニシアチブということもご紹介くださいました。で、その中でユタ州に関しての取り組みに教えていただきたいんですけれども、風力との統合の中で、例えば風力で起こるそのエネルギー供給の変動をこの SMR で吸収しようとされているとか、ユタ州における統合的な電力の研究の取り組みをもう少し教えてください。でもう一点質問なんですけれども、先ほど枝広委員からもありましたが、立地に関してなんですけれども、外部の例えば電力、外部の水は不要ということでした。ということは内陸の例えば湖とか川に接していないいわゆる本当の内陸地でも問題ないと、排熱の観点からも問題ないとお考えでしょうか。で、次がスタンフォードのマジマダール教授ですけれども、グリッドの話大変下に飛んでおりまして、でその中で産業用の熱はただ脱カーボンが難しいというお話もありました。でエネルギーを考えたときに、電気と熱と、完全に独立して考えるのではなくて、一緒に考えられるところは考えるべきだと私自身は思うのですけれども、例えば産業用の熱に関しまして脱カーボンに関して何か示唆があれば教えてください。以上。